Morning, everyone. Let's wait a few minutes till everybody comes in. Questions in the meantime? How's everybody doing? Does the sound good? Everybody can hear me? Thank you. What we're going to do, we're going to start with sequences and series again. So from the beginning, if you weren't in Math 141 last semester, no issues. If you were, there's going to be a bit of an overlap. But since we didn't get that far into the topic anyways in 141, it's 1 or 2 days of overlap. It's not going to be a big issue. Plus, it'll serve as a refresher since, it has been a month. I've posted the course outline on my courses. Have a look at that if you haven't seen it yet. Essentially, it says we'll have web work assignments. I've posted a link to web work already. Assignment 0 is up. It's not for marks. It's just a tutorial on the web work system. If you've never seen web work, you might have a look at it. If you have seen it, then you know that there's nothing there for you to do. So web work assignments were 30%. We'll have a midterm scheduled for Friday of next week. We're 30%. We'll do a 72-hour midterm and a final exam during the final exam period. Again, one of those 72-hour deals that you're familiar with already by now. So speaking of the exams, for those of you who were in 141 last semester, you understand that we're trying to make the exam so that you can't just look up the answers on Wolfram Alpha. So the exams are built in a way that you need to think. The questions aren't taken directly from the book. They're a bit different than what you might be used to. So the question naturally comes up, how do you prepare for this course? How do you make sure that you're comfortable with the material, given that the exams will take on a different look than they would if they were in-person sit-in exams? Well, I want to suggest that there's no difference in preparation. You need to master the material. If you're comfortable with the material, the exam should go relatively smoothly. I'm sure you've all seen the comments on certain websites that suggest the Math 141 exam was unfair. It was this, it was that. There were too many proofs. In fact, if you wrote the 141 exam, you know very well there was not one single proof on the exam. So I don't know where that's coming from, but there it is. And again, there will be no proofs on the 262 exams. The questions, however, will be different from just regular exercises, because you could always just look those up on Wolfram Alpha. So that's how the exams will differ, but it's not an issue if you're comfortable with the material. And how do you get comfortable with the material? Lots and lots of exercises from the book. So for those of you who don't know my teaching style, I will present the material theoretically, maybe do a few proofs if the proofs are nice and easy, or if they bring something more to the understanding of the issue. And then we'll do lots of exercises from the book. What you need to do after each lecture is go home, or, well, I mean, you're already there, and do lots of exercises from the pages we covered. We'll do the even questions because the odd questions have answers in the back. You should go home and do all the odd numbered questions in the book. This way, you're going to master the material, and you can treat web work as a test of whether you know the material or not. If you're comfortable with the material, web work should be very easy. The course will be recorded. So exactly what we're doing now, I'll post a link after the course, after this lecture is done, to my courses. So yeah, so lots and lots of exercise from the book. That's how you learn these low-level math courses. And you know, I mean, whether or not it's a typical course where you have final exams in the gym, or whether it's a 72-hour take-home exam, you learn the material in the same way. So if you're comfortable with the material, there's no reason for you not to do extremely well in this course without resorting to Wolfram Alpha or looking anything up, really. Questions, anyone? So today we're going to start from the beginning. We're going to start with sequences. And what is, well, before we do that, maybe I'd like to share one more thing. I know some of you are maybe thinking about doing two courses simultaneously. Sounds like a good idea. Getting two courses out of the way in the summer, plus you've got that 72-hour final exam period, and the exams are take-home. Sounds very reasonable. Don't do it. Don't do it. It's a bad idea. This course is relatively straightforward, and there's no reason for you not to get an A in this course if you put in the work. If you are doing two courses at the same time, you just don't have time to learn the material. And you're always finding yourself cutting corners and doing one stuff in one course versus stuff in the other, and it's just a big mess. Do yourself a favor, don't do two courses at once. I have absolutely no, so somebody's asking if I can make the web work a bit more similar to the exam questions. I cannot change the web works. They're already set up. I have no input into those. The assignments are already made, and yeah, so there's nothing I can change there. Any updates for Math 141? The marking is painfully slow. So that's the update. I don't know when the marking is going to be finished. I would hope that by the end of the week, everything will be done. That's my hope. I can't guarantee that though. The marks, as I expected and as I'm sure you expect, are insanely high. Almost everybody has 100%. I'm sure the average, last time I checked, the median for each question was 100%, which means that more than half, well, at least half the class got 100% on each question. That was it last time I checked. So somebody's asking if the marks will come out before the satisfactory, unsatisfactory thing is concerned. Satisfactory, unsatisfactory deadline. When is that deadline? Is it the 15th? I seem to recall it being May 15th. If somebody could, yeah. Well, so somebody's saying now May 22nd. I can say with confidence that the marks should come out before May 15th. I will push everybody to make sure that the marks come out before May 15th. So if it's May 22nd, then you have even more time, but I'll make sure everything comes out before the 15th. Let's get to work with sequences. What is a sequence? A sequence is just a string of numbers. It's a list of numbers in a specific order. So definition, a sequence is a list of numbers in a specific order. So a list of numbers in a specific order. Let's take an example. The numbers 1, 1/2, 1/3, 1/4, and so on, right? I mean, this is the first number of the list, the second, third, and so on. You may recognize that sequence, right? I mean, there is a nice way to describe the sequence. This is the sequence 1 over n, where n goes from 1 to infinity, right? When n is 1, you have the first term. When n is 2, the second. When n is 3, and so on and so on. Let's take another example. The sequence 1, 0, 2, 0, 3, 0, 4, 0, and so on, right? Again, a list of numbers in a specific order. This is the first term, second, third, fourth, fifth, and so on and so on. Here, it might be difficult to describe in a nice general format, but it doesn't matter. It's still a sequence. And there it is. Let's take another example. Consider the sequence 2 to the n over n squared, where n goes from 1 to infinity, right? What is that? So when n is 1, this is 2 over 1. When n is 2, this is 4 over 4. Or 1. When n is 3, this is 8 over 9. When n is 4, 16 over 16, and so on and so on. In general, a sequence, right, I mean, looks like this, or the sequence has the form an, where n is a natural number. Which really suggests a different or a second definition of a sequence. Right here we've described it as a list of numbers in a specific order, but this is not the real definition. I mean, it's fine, but we have an alternate definition. A sequence is really a function. From the natural numbers to the reals. Right? Where f of 1 is your first term. F of 2 is your second term. And so on. F of n is your nth term. So this sequence is really a function. When you plug in the natural number 1, you get your first real number. When n is 2, your second, and so on and so on. So a sequence is really a function from the natural numbers to the reals. And that is the limit as n goes to infinity. How does this function behave for large values of n? So what are we interested in? All we want is the limit as n goes to infinity of a to the n. That's all we're interested in. If that limit exists, and is a real number L, we say the sequence converges to L. If the limit is some sort of infinity, if L is positive infinity or negative infinity, we say the sequence diverges to infinity or negative infinity. And if the limit does not exist, we say the sequence diverges. Or you could be more specific and say the sequence does not converge, meaning that there is no limit, but regardless. If the limit does not exist, we say the sequence diverges. Now, in this definition of limit, we're restricting our attention to the natural numbers, right? Because the sequence is only defined for the natural numbers. Remember, the sequence is a function from the natural numbers to the reals. Now, of course, if your expression makes sense for real numbers as well, so, right, I mean, if you have a function defining your sequence, and if your function is defined for real values, for all real values, and furthermore, and if the limit as x goes to infinity of f of x exists, then, of course, the limit as n goes to infinity will exist and be the same. Meaning that everything you know about limits extends to limits of sequences if this is true, if your function can be extended to the real numbers. What am I talking about? I'm talking about L'Hopital's rule. I'm talking about the squeeze theorem. I'm talking about epsilon delta definition. Moreover, you know that the limit of a sum is the sum of the limits if both limits exist. So here, if you have two convergent sequences, then their sum is also a convergent sequence, and the sum converges to the sum of both limits. Same with a product, same with a quotient, and so on and so on. But of course, you already knew all of this, right? This is stuff we saw last semester. Let's take a few examples from the book. Questions, anyone? Says I'm unable to connect to the chat. I don't know what that means. I think it's working. All right. Let's take a few examples from the book. The question is asking us to find a formula for the following sequence, right? So we're given a sequence here. Can we describe this in a nice closed form? Can we display a formula that will give us these values when n is 1, when n is 2, 3, and so on and so on? Well, I mean, let's forget this for a moment and just look at these. Here, I'm sure, of course, you recognize the denominator as powers of 4, right? 4, 4 squared, 4 cubed, and so on. So that's going to give us an idea Moreover, negative, positive, negative, positive. You've seen this before, where the terms alternate between positive and negative. Do we have an idea of a formula for this? Anybody? Is my chat actually working? Perhaps the chat is not working. Can somebody write something on the chat? Is this even... Uh-oh. The chat doesn't seem to be working. I'm just checking my email in case there's some other issues. If there's an issue, please send me an email. There might not be an issue. Maybe just an issue with the chat. I'll see if we can fix that for tomorrow. Otherwise, we'll bring up some other chat room. Yeah, my chat's not working. All right, anyways, let's keep going. Somehow the chat's not working, but we'll see. So, you've had time to come up with a formula for this, I'm sure. What were we saying? Powers of 4 in the denominator, alternating between negative and positive. So let's take the alternating business, -1 to a power n. But of course, if n is 1, this is going to be negative. So let's say -1 to the n plus 1 to make sure you're starting out with something positive. And these are going to be powers of 4 in the denominator. This is when n is 3, you have 4 to the 1. So this should be probably n minus 2. Let's try. We're just trying something. May or may not work. When n is 1, this is -1 squared, which is 1. And this is 1 over 4 to the -1, which is 4. Looking good. When n is 2, this is -1 cubed, which is -1. 2 minus 2 is 0. So you have -1, and so on and so on. When n is 3, -1 to the 4, which is 1, over 4 to the 1, which is 4. Looking good. Let's try another one. Really like to connect to that chat here in case there are questions. That's not working. Anyways, let's not waste any time on that. Here it is. We're just trying to find a nice formula for this. Going to give you a moment to try to work that out. What do we notice? From 5 to 8, there's a difference of 3 here. From 8 to 11, there's a difference of 3. 3, 3. So you're just, I've popped out the chat room, and it's working quite well there. Very good. So 5 plus 3n was the suggestion. 5 plus 3n works very nicely if you start n at 0, which is fine. You know, I mean, we said sequences were a function from the natural numbers to the real numbers. You could throw in a 0 there, and it's all good. So here we go. When n is 0, you're starting out with 5. When n is 1, you've got 8. When n is 2, 11, and so on. Very nice. Very nice. Let's do one more. Consider this. So again, we're looking for a formula to describe this. And somebody kind of gave it to us, suggesting sine of n pi. The problem with this, was it sine of n pi or sine of n pi over 2? And I think that does it. When n is 1, this is sine of pi over 2, which is 1. When n is 2, it's sine of pi, which is 0. When n is 3, it's sine of 3 pi over 2, which is negative 1, and so on and so on. Very nice. So your sequence can be described in this way. Well done. There may be more than one right answer, right? So it's not necessarily unique, and it doesn't matter. As long as you can describe it in some way, we're good to go, and this works out very nicely. Let's move on to asking the question, do these sequences converge or diverge? And there it is. So what are we interested in? We just want to evaluate the limit as n goes to infinity. Does this limit exist? And if so, what is it? So limit as n goes to infinity. I'm sure you've recognized that this has the form infinity over infinity. We could do a L'Hopital's rule, right? Because this makes sense when n is replaced by x. Or, as suggested, let's factor out the largest power of n on top and on the bottom. Well, on top it's already factored. Let's factor out a root n from the denominator. And what do we get? We get a 1 plus 2 over root n. Now the root n's cancel out nicely. And as n goes to infinity, root n goes to infinity, 2 over infinity is 0, leaving you with a limit of 3 over 1, or 3. Exactly that. Consider this. The sequence 4 to the n over 1 plus 9 to the n. Again, all we're interested in is what is the limit as n goes to infinity. And once again, this has the form infinity over infinity. So let's do what we did here. Let's factor out. Let's factor out a 9 to the n from the denominator. What do we get? We get a 1 over 9 to the n plus 1. Or, if you prefer, if we group these two things together, this is 4 over 9 to the n times this. Now, as n goes to infinity, 9 to the n, you're taking larger and larger powers of 9. This is going to go to infinity, and 1 over infinity is 0. So this goes to 0. In other words, this fraction here goes to 1. So if this limit exists, then the limit of the product is going to be the product of the limits. Tempting to use geometric series here, but remember that this is not a series, but rather a sequence. So it's different, right? We haven't gone to series yet, but we will in a few moments. So really the question is, what is happening to 4 over 9 to the power n? Well, I'm sure most of you know the answer already. Right? And it was suggested to take the ln. Let's investigate what is this limit. What is that limit? Well, we're going to work out that limit by taking the ln. What does this do? This allows us to bring the n down. First of all, notice that these two things are not the same. I've changed the question by taking a ln, so there's no equals here, they're not the same. But this allows me to bring down the power And as n goes to infinity, this is just a number. So the limit is going to be infinity times whatever number that is. And as n goes to infinity, really what is that number? Well, if you look at the graph of ln that you know, the graph of ln crosses the x-axis when x is 1. So 4/9 here is going to be a number less than 1. So ln of 4/9, who knows what that is, but for sure it's less than 0. So this is a negative number times infinity. So the whole thing is negative infinity. And consequently, this goes to e to the negative infinity. Right? We're going to compensate for having taken the ln by taking the exponential, because you know exponentials and lns are inverse functions of each other. They cancel out. So this is e to the negative infinity, which is everyone? Exactly that, which is 0. Notice that this is not specific to 4/9. In fact, if you have any number here that is between 0 and 1, so if you take any number between 0 and 1, a to the n is going to go to 0 as n goes to infinity. You can repeat exactly this argument for any value between 0 and 1. And in fact, if a is between -1 and 0, then a to the n, what is a to the n? It's going to be between 0 and no. Actually, let me not go into this right away. Let's not worry about this for now. I'll take this up again in a moment. My point was that you could conclude the same thing for a between -1 and 0, but we'll do it in a different way in a moment. Let's just look at a few more sequences here. There it is. Again, the question is, what does the sequence converge to? Or does the sequence converge? And if so, to what? So again, we're just looking at the limit as n goes to infinity. And this has the form infinity over infinity. We can apply L'Hopital's rule, right? Because this ln of n and ln of 2n makes sense if n is replaced by x, right? So you don't have to restrict your attention to natural numbers here. This makes sense in the context of real numbers as well. So if we apply L'Hopital's rule, treating n as an x, derivative of ln is 1 over, derivative of this is 1 over, times the derivative of the inside, chain rule, right? Which is just the limit of 1, which is 1. There it is. Consider this. What does this sequence converge to? So we're looking at the limit as n goes to infinity of arctan, right? And as n goes to infinity, arctan of infinity, you know to be pi over 2, precisely. So this has the form pi over 2 over infinity, which you know to be 0. Plugging in is the way to go here, right? And it's something you should always be doing when you're looking at limits anyways. It's really your first step. Here it gives you the answer. All right, consider this. Or if you prefer, cos of n pi over 2 to the n. Why don't we take a moment to investigate this cosine of n pi for a moment? There's an interesting observation to be made here, one which we'll use over and over again in this course. Let's just look at this starting at 0. Just the sequence cosine of n pi, what is that? When n is 0, cosine of 0 is 1. When n is 1, cosine of pi is -1. And when n is 2, cosine of 2 pi is 1, and cosine of 3 pi is -1, and so on and so on. So this sequence is this string of numbers, and you see what's happening, right? It alternates between +1 and -1. But we've seen another sequence that does exactly that, namely -1 to the n, right? Starting at 0, this is 1 and -1 and 1 and -1 and so on. In other words, cosine of n pi is exactly the same as negative 1 to the n. A very nice observation that we're going to use over and over again. So might as well make it here, and might as well use that here. So we're really looking at the sequence negative 1 to the n over 2 to the n. All right? And the question is, what is this limit? Well, I mean, if we were to take a limit as n goes to infinity, just to see what's going on, because I mean, this is the answer we're trying to, this is the question we're trying to answer anyway. As n goes to infinity, 2 to the n goes to infinity, but the numerator doesn't exist. So this is a limit that has the form does not exist over infinity. So let's work out this limit by getting rid of our problem, right? The numerator is the issue because the limit of the numerator does not exist. So let's get rid of the numerator. Negative 1 to the n, well, I mean, it's either 1 or negative 1. So it's either 1 or negative 1, so it's less than or equal to 1, and it's bigger than or equal to negative 1. And if we multiply the whole thing, the whole inequality by 1 over 2 to the n, which is always positive, so the inequality remains the same, and we get negative 1 over 2 to the n, less than or equal to negative 1 to the n over 2 to the n. And now, as n goes to infinity, 2 to the n goes to infinity, so this is 1 over infinity, which is 0. Here, it's negative 1 over infinity, which is still 0. So by the squeeze theorem, this goes to 0. This converges to 0 by the squeeze theorem. How are we doing here? Questions? Too easy? Do we want to do one more? Let's do one more. You're right that there was actually no need to observe that cosine n pi was negative 1 to the n. You could have squeezed cosine n pi between negative 1 and 1 regardless, but it was a nice observation to make at this point, and one that we'll use over and over again in the course. Consider this sequence, n to the 1 over n, and again, you know, let's, if you want, we could just get a feel for this sequence, right? When n is 1, the whole thing is 1, and then it's square root of 2, and then it's 3 to the 1/3, cube root of 3, and so on and so on, 4 to the 1/4, 4 to the 1 over 4. Again, the question we wish to answer is, what is the limit as n goes to infinity. And let's just plug in, see what's going on here. As n goes to infinity, this has the form infinity to 0. Which you know to be an indeterminate form, right, from your work in Cal 1. And you know exactly what to do here. How do we treat this? We treat that by looking at the limit of the ln. Again, you're taking the ln, so you're changing the question. These are not equal. And what does that allow you to do? That allows you to bring the 1 over n down. And you can rewrite this as ln n over n. And as n goes to infinity, this has the form infinity over infinity. This has the form infinity over infinity. What are you going to do? L'Hopital's rule, of course. Derivative of the top, derivative of the bottom. Limit is Roy, this is Cal 3, Calculus 3. Limit is 0, thank you. And consequently, the original limit, we had changed the question by taking a ln. We're going to compensate by raising everything to the exponential. Limit is 1. There it is. Questions here about sequences? Let's take a moment to introduce the factorial for a natural number n. We define n factorial denoted by n with an exclamation to be the product of all the numbers 1, 2, 3 all the way to n. Let's say a few examples. 1 factorial is just going to be 1. 2 factorial, 1 times 2, which is 2. 3 factorial, 1 times 2 times 3, which is 6. And so on, right? 4 factorial, 1 times 2 times 3 times 4, which is 24, and so on, and so on. Let's take a moment to extend this to 0 because it's convenient. 0 factorial we define to be 1. So there it is. 1, 2, 3, 4 factorial. I'll let you work out what 5 factorial is, but you'll see that it's 120 and so on and so on. Why don't we take a moment to do 1 or 2 examples with the factorial. Consider what we're defining 0 factorial to be 1. Just for convenience, right? I mean, I've rubbed it off now, but n factorial was only defined for natural numbers. Here I'm suggesting that we're going to extend it to 0 and say that 0 factorial is 1. Well, I mean, it's not really a proof. We're defining it. We're defining it to be 1. Because you'll see that it's very convenient. Let's take a few examples. First, let's consider the sequence 1 over n factorial. 1 over n factorial. Let's write out the first few terms just to get an understanding of that. When n is 0, it's 1 over 0 factorial, which is 1. When n is 1, it's 1 over 1 factorial, which is again 1. When n is 2, 1 over 2 factorial, which is 1/2. When n is 3, 1 over 6, and so on and so on. You see what's happening, right? What can we say about the convergence of the sequence? Does this sequence converge? And if so, to what? What is happening to the denominators there? Right? Denominators are getting larger and larger, right? This is the product. 1, 2, 3, 4, all the way to n. So these denominators are getting larger and larger, going all the way to infinity. 1 over infinity is 0. Questions here? Anybody? How are we doing? Very well. Let's move on. Let's move on from sequences into series. You know what's going on there, but do exponentials, exponents expand quicker than factorials? It's a good question. The answer is no. The answer is no, no, no. And it's such a good question that we'll discuss it now. Consider the sequence 2 to the n over n factorial. Let's just write out the first few terms just to understand what's going on here. And starting at 1, say. So when n is 1, this is 2 over 1. When n is 2, this is 4 over 2, which is still 2. When n is 3, it's 8 over 6, or 4 over 3. When n is 4, it's 16 over what now? I've lost track. Over 24. 16 over 24. And so on and so on. So it seems that the numbers are getting smaller, but you know that that's not a proof. Let's prove it now. This 2 to the n over n factorial. First of all, factorials are always positive. Exponentials are always positive, so this is bigger than or equal to 0. And what is this? This is 2 times 2 times 2, n times. And this n factorial is 1 times 2 times 3 all the way to n. And observe that all of these fractions are each less than or equal to 1. So I can replace, I'll leave the 2 over 1 there. And this 2 over 2 is just 1. And this 2 over 3 is less than or equal to 1. And then you'd have 2 over 4. All the way to the last one, which I'll leave as 2 over n. So you see that this expression is less than or equal to 4 over n. And as n goes to infinity, 4 over n goes to 0. This goes to 0. So this expression goes to 0 by the squeeze theorem. Very nice. All right. Questions? A very nice question, but this shows that the factorial is increasing faster than 2 to the n. And you can, again, 2 to the n is nothing special here. You can repeat this argument for any number to the power n. So factorials grow faster than exponentials. Yes, this list is correct. Somebody's giving us a list. Not something I expect you to remember by heart, but something that you can prove in exactly the same way. Very nice. All right. Moving on. Moving on to series. And again, some of you have experience with those. We've seen them in 141, at least the beginning, but perhaps some of you have not done these before. What do series refer to? Series are infinite sums. Now, the ancient Greeks did not believe you could add infinitely many positive numbers together and get anything other than infinity. But this simple argument will convince you otherwise. Suppose you had a pie and that you ate half the pie. and then you ate half of what remains. And then half of what remains. And so on, keeping, where you keep eating half of what remains. You never run out of pie. Conversely, if you take a number between 0 and 1, this can be viewed as a portion of the pie. If you measure this from the North Pole, if you will, clockwise, if A is very close to 1, if you've got almost a whole pie, by eating half of what remains, you eventually surpass A. So this has to be bigger than any number less than 1. So this has to be at least 1, but it's at most 1, so it has to be 1. Let's introduce shorthand notation for these series. Right? This is the series 1/2 plus 1/4 plus 1/8 and so on. Shorthand notation, or the sigma notation that you've seen in Cal 2 with Riemann sums and such. Right? This is the series 1/2 to the n. What does that mean? When n is 1, this is 1/2, plus when n is 2, 1/4, plus when n is 3, 1/8, and so on and so on. And this argument suggests that this sum is actually 1. Let's take another example. The series 1/n squared. What does this refer to? So series, again, sigma notation here, it's a sum. When n is 1, this is 1/1 squared, or 1. Plus when n is 2, 1/4. Plus when n is 3, 1/9. And so on and so on. What do series look like in general? Series look like this. That's what a series looks like. And you see the issue, right? I mean, we were just looking at sequences. Which have this form. They look very much alike, so you have to be very comfortable distinguishing the two. Right? Here, all you're interested in is the limit. Here you have a sum. And I mean, you see the obvious relationship. In a series, you are adding the terms in a sequence. But there's a much more important relationship between sequences and series. Given Given a series, so somebody's asking a question here. So basically, if the limit of the sequence AN converges to 0, then this series will converge to 1. That is incorrect. Just because the terms converge to 0 does not mean the series converges to 1. In fact, it does not even mean that the series actually converges. We'll see some examples momentarily, but I was suggesting that there's an obvious correlation between sequences and series, where in a series you are adding the terms in a sequence. That's an obvious relationship, but it's not the important one. Given a series, so given a series AN, we are going to construct a sequence. We construct a sequence known as the sequence of partial sums. So we construct a sequence Sn. We construct a sequence of partial sums Sn where S1 is the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms, and so on and so on. Sn is A1 plus A2 all the way to An. It's the sequence of partial sums. You're only going all the way up to n. And right, so we have constructed a sequence of partial sums, and we say that the series converges. The series converges if and only if the sequence of partial sums converges. So you see what this does. And well, I mean, let me add, in this case, they converge to the same value. So you see what this does, right? This translates this new object, a series, into a sequence. So into a sequence that we have experience with, that we know how to deal with. So it rewrites this new object in terms of an old one. And everything we know about sequences is therefore going to apply to series, because a series is really just a sequence of partial sums. So in particular, you know that if you have two sequences that converge, then their sum converges, and it converges to the sum of the two limits. Well, same thing for series. If you take two series that converge, then you can build a new series, which is the sum of the original two, and that series will converge as well, and it will converge to sum of whatever the original two converge, and so on and so on. So everything you know about sequences extends to series. Let's consider an example of this sequence of partial sums by considering our first example, which may or may not have convinced you originally. Consider the somebody's asking where Sn is the sum from 1 to n. What was the question here? Perhaps that was not meant for me. Consider this. Let's take a moment to write out the sequence of partial sums. So S1 is the first term, which is 1 over 2. S2 is the sum of the first two terms. One over 2 plus 1 over 2 squared. S3 is the sum of the first three terms. And so on and so on. Sn is the sum of the first n terms. Right? Some of you have certainly recognized this as a convergent geometric series, but where we're going with this is that there's a nice closed form for this Sn term. Observe what happens if you multiply Sn by 1. You know that if you multiply something by 1, it does not change the term. We're going to multiply Sn by 1 minus a half over 1 minus a half. You're multiplying by 1, you're not changing anything. And observe what happens if you do that. If we multiply Sn by 1 minus 1/2 over itself, it doesn't change the expression. But let's do the multiplication. 1 times every term here. So you're going to have all those terms again. And then minus a half times every term. So you get minus 1 over 2 squared. Minus 1 over 2 cubed, all the way to minus 2 to the n plus 1. The whole thing divided by 1 minus 1/2. And observe what happens. I mean, I'm sure a lot of you have seen this before, right? But the 1 over 2 squared cancel out. And the term after 1 over 2 squared would have been 1 over 2 cubed. And that would cancel out with this one. Everything would cancel out. The term before 1 over 2 to the n plus 1 would have been a minus 1 over 2 to the n, which cancels out with this one. So almost everything cancels out except this 1/2 and the minus 1 over 2 to the n plus 1. So you see, you have this nice closed form for Sn. Now this process of canceling things out is known as a telescoping sum. Like the old-time pirate telescopes, right, that would collapse upon themselves. And there it is. You have this nice closed form for Sn. Somebody's asking, what if you multiply by 1/2 instead of 1 minus 1/2? Well, exactly, right? If you multiply just by 1/2, you wouldn't have this nice canceling out of terms. So that's why it's important to multiply by 1 minus 1/2 over itself, not just 1/2 over 1/2. Right? It's that telescoping sum idea that is important, and that allows you to have a nice closed form for Sn. And now, what is the limit of Sn? What happens as n goes to infinity? Well, the only thing that depends on n is this term right here. And as n goes to infinity, 2 to the n plus 1 goes to infinity, 1 over infinity is 0. So this goes to 0. So you're left with 1/2 over 1 minus 1/2, or 1/2 over 1/2, which is 1, exactly what you knew it would be, right? Because originally, in our pi example, we convinced ourselves that this series converges to 1. So there it is. How did we decide to use 1/2? Well, I mean, we're asking ourselves, is there something that gives us this telescoping sum? Well, we'll take another example, and this will illustrate it very nicely. Well, there it is. Right, the sequence of partial sums converges to 1, so the original series converges to 1 as well. Let's take an example. Let's take another example. Consider the sum starting at 0 now of 1 over 3 to the n. So let's work out the sequence of partial sums. S1 is the first term. So when n is 0, first term is? Anyone? Well, I mean, we're getting to geometric series. This is our next step. We're going to find after this example, we're going to find a general formula for geometric series and introduce the term, actually, because, you know, we haven't even introduced that yet. So S1 is the first term, which is 1. S2 is the sum of the first two terms, 1 plus 1/3. S3 is the sum of the first three terms, and so on and so on. Sn is the sum of the first n terms, all the way to 1/3 to the n minus 1 this time, right? Because we're starting with the 0 term. Again, this has a nice closed form. If you multiply this by 1, you don't change anything. What 1 are we going to use? Think about it. To get some sort of telescoping business. 1 minus 1/3 over 1 minus 1/3. Let's work that out, see what happens. So let's multiply each term by 1. What do we get? All the way to 1/3 to the n minus 1. And then if we multiply by negative 1/3, we get minus 1/3, minus 1/3 squared, all the way to minus 1/3 to the n. The last term is 1/3 to the n minus 1 because we actually started at 0 here, as opposed to starting at 1 in the previous example. Right? So, I mean, let's look at what's happening here. This is 1/3 to the 1, not 3 to the 2. 3 to the 1, 3 to the 2, as opposed to the subscript. So the power is 1 less than the subscript. The subscript is n, 1 less, n minus 1. All over 1 minus 1/3. And let's see what cancels out here. Right, the 1/3s cancel out. 1/3 squared cancel out. Everything cancels out. The term before minus 1/3 to the n would have been minus 1/3 to the n minus 1, which is canceling out with this one. So again, you've got that telescoping sum idea. What are we left with? 1 minus 1/3 to the n over 1 minus 1/3. And again, limit as n goes to infinity. As n goes to infinity, the only thing that depends on n is this, and it's easy to see that this goes to 0. Leaving you with 1/2 or 3/2. So this series converges to 3 over 2. Can we repeat in general? What if you took any number to the power n? Right? I mean, we've done it with 1/2 to the n. We've done it with 1/3 to the n. Can we repeat for a to the n in general? Where a is not 0. Right? Because we don't want to have this issue of 0 to the power 0. What is that? Let's not worry about it. So let's make sure a is not 0 to begin with. And what is S1? S1 is the first term, a to the 0, which is 1. S2 is the sum of the first two terms. So 1 plus a. S3 is the sum of the first three terms, 1 plus a squared. And so on, Sn, 1 plus a squared, all the way to a to the n minus 1. Again, convention, because we're starting at 0 again. Why is the last term a to the n minus 1? Because we're starting at 0. Look at what's happening, right? This is a to the 1 compared to the subscript 2, so it's 1 less. A squared compared to 3, 1 less. 1 less than the subscript. We're going to multiply this by 1, a good one, so that we get some sort of telescoping sum again, where everything kind of cancels out. What 1 am I referring to? One minus a over itself. Here, it's understood that the denominator is not 0, so a should not be 1. So let's throw that in as well. A should not be 1. Because you don't want the 0 over 0 here. You want to be careful. So this trick is going to work if a is not 0 or 1. And what happens if you multiply by 1 minus a over 1 minus a? Exactly the same thing as what happened in the case 1/2, or in the case 1/3, that I'm conveniently erasing now. Multiply by 1. Multiply each term by 1. So 1 plus a squared, all the way to a to the n minus 1. And then multiply by negative a. So minus a squared, all the way to minus a to the n. Where the term before was minus a to the n minus 1. And you see that a lot of things are going to cancel. The a's cancel out. The a squares cancel out. Everything cancels out. The term before this was a to the n minus 1. So that's going to cancel out. Almost everything cancels out. Again, you've got that telescoping sum idea, except the 1 is still there, and the a to the n is still there as well. And now we ask the question, What about the limit as n goes to infinity? Again, the only term that depends on n is this one right here. Somebody's asking why a equals 0 matters. Well, the only question that comes up is if a is 0, what does 0 to the 0 mean? And that's really the only issue that we have, because for other powers, 0 to the 1, 0 squared, 0 cubed, all of those are 0, so there's no issue there. But the first term, 0 to 0, is slightly questionable. Again, the question arises, why is the last term a to the n minus 1? Well, since we're starting at 0, the first term is 1. S2 is the sum of the first two terms. Observe that the power of a is 1 less than the subscript. A squared versus a cubed. 2 is 1, so it's 3 minus 1. 2 minus 1 here. So n minus 1. Right, so now we're looking at this limit, and the only thing that depends on n is this term right here. If this was a fraction, either positive or negative, then this is going to go to 0. So if a is between -1 and 1, this goes to 0. It's a fraction, and if you take larger and larger powers of that fraction, it goes down to 0. If a is bigger than 1, like 2, 3, or pi, or root 2, anything bigger than 1, when you take larger and larger powers, that's going to go to infinity. And similarly, if it's less than -1, then this is going to alternate between a large positive number and a large negative. So the limit will not exist. And same if it's -1 to the n. It alternates between +1 and -1. The limit does not exist either. So we get this nice result that this limit exists if and only if the value of a is between -1 and 1. And in this case, the limit, this goes to 0, so you're left with 1 over 1 minus a. Now, this result is so important, and these series are so important that we give them a name. Definition: a series of the form is known as a geometric series. So a series of the form a to the n is known as a geometric series, and the series converges to 1 over 1 minus a if a is between -1 and 1, or if absolute value of a is less than 1, and diverges otherwise. The second example. E to the negative n. The series e to the negative n. Or if you prefer, the series 1 over e to the n, which is the same as 1 over e, the whole thing to the n. So now, having rewritten it this way, you recognize it as a geometric series, where e is 2.71 something something. So this is a fraction close to 1/2. So 1 over e, an absolute value is less than 1. So it's a convergent geometric series. What does it converge to? Well, our formula tells us it's 1 over 1 minus 1 over e. Or, if you prefer, e over e minus 1. How are we doing? Questions? Well, let me ask you a question. What if, instead of starting the sum at 0, what if you started somewhere else? What if you started somewhere else? What if you started at 117 to infinity? Certainly, the convergence is not affected. Whether or not the series converges, the recorded video will be uploaded. It'll be both on YouTube, and I'll post a link on my courses. Assuming nothing goes wrong with the video recording, right? I mean, we never know. But I think usually YouTube is pretty reliable, so everything should be fine. What if the sum started at 117? How does that affect the series? Well, it does not affect whether the series converges or not. What it does affect is what it converges to, right? Think about it. This is 1 plus 1 over e plus 1 over e squared, and so on, forever, whereas this starts at 1 over e to the 117. Right? I mean, at some point, you get the overlap between these two, but this one, the sum is going to be a lot larger. Right? So the question is, how do we take care of that? Well, I mean, observe. I've written it out here. 1 over e to the 119 and so on. If we factor out a 1 over e to the 117, observe what happens. This is just 1. And here you get a 1 over e to the 1. And here you get a 1 over e squared. And so on and so on. And this is exactly that. So this converges to 1 over 1 minus 1 over e. Because that is the original geometric series starting at 0. So in other words, this converges to 1 over e to the 117 over 1 minus 1 over e. In other words, it's the first term over 1 minus 1 over e. Right? Where here the first term was 1. So 1 over 1 minus e. So it's always the first term. We can generalize that. Well, I mean, let me write it as a claim. If you start at any value k, this is going to be the first term, a to the k over 1 minus a, if a is less than 1 in absolute value. Why is it 1 over e to the n and not 1 over e to the n minus 117? Did you mean here? Right, I mean, I factored out a 1 over e to the 117. So, I mean, I get a 1, and then a 1 over e to the 1 over e squared, and so on. I haven't introduced any n's here. Right, I haven't introduced any n's. I'm not rewriting it in a series notation, only pointing out that this is the original series from 0 to infinity. So we're good to go. So there you go. I mean, if you have a geometric series, you can actually have it start at any place k, and it converges to the first term. This is always true. Very nice observation. Now, this idea of telescoping sums can also be found outside of the geometric series. Consider the series 1 over n squared plus n. If you write out the first few terms, right, this is 1 over 2. And then when n is 2, 4, 5, 6, 1 over 6. And when n is 3, 9, 1 over 12. And so on and so on. It's not really clear what's going on. But if you rewrite this, if you consider the 1 over n squared plus n, which is really 1 over n times n plus 1, if you apply partial fractions to this, this decomposes as 1 over n minus 1 over n plus 1. Right, let's just convince ourselves, if you put everything back over a common denominator, you get n plus 1 minus n, so you just get a 1 over the product, exactly what we had to begin with. So we're really looking at the series 1 over n minus 1 over n plus 1. Let's work out the sequence of partial sums. How do we get this? Do the Partial fraction decomposition. Perhaps that was not a question, but very well. So S1, let's work out the sequence of partial sums. S1 is the first term, so that is 1 minus 1/2. S2 is the sum of the first two terms. So 1n is 1 plus 1n is 2, 1/2 minus 1/3, and observe that these cancel out, leaving you with 1 minus 1/3. S3 is the sum of the first three terms. So plus 1/2 minus 1/3 plus 1/3 minus 1/4. And the 1/2s cancel and the 1/3s cancel, leaving you with 1 minus 1/4. And so on and so on. I think we can see a pattern. Can we guess at what the general pattern is, right? 1 minus S2 is 1 minus 1/3. S3 is 1 minus 1/4. Sn is I understand there's some people writing comments on the chat board. Please disregard them. If they're not in our class and they're just here to disrupt, I mean, yeah, exactly. Let's not worry about them. What is Sn? Sn is 1 minus 1 over n plus 1. I saw it. Thank you. And as n goes to infinity, this is easily seen to converge to n plus 1 goes to infinity. 1 over infinity is 0. So this term goes to 0. The whole thing converges to 1. And there you go. This sum, this series, converges to 1. So we have this telescoping sum idea again here outside of the context of geometric series. Very nice. Now, if we take a step back and look at what we've considered so far, we saw a few convergent series, 1 over 2 to the n, 1 over 3 to the n, 1 over e to the n, and right here, 1 over n squared plus n. We've all worked out what these series converge to. These are all examples of convergent series. What do all of these have in common? The terms you are adding are getting smaller and smaller, closer and closer to 0. As n gets very large, these terms are very close to 0. Is this a coincidence? It is not. And the result is known as the divergence test. If the limit of the stuff you're adding is not 0, then the series AN diverges. Think about why that is. Suppose the limit is 1. Suppose the limit is 1, then what is this series? For large values of n, if the limit is 1, that means that an is very close to 1. So here, the series is like adding 1 plus 1 plus 1 plus 1 infinitely many times. What are you going to get? You're going to get infinity. 1 plus 1 plus 1 plus 1 infinitely many times gives you infinity. If the limit is something else, like 1 over 10, then this means that for large values of n, an is going to be close to 1 over 10. So here, you'd be adding like 1 over 10 plus 1 over 10 plus 1 over 10 infinitely many times. Well, if you add 1 over 10 10 times, you get 1. And then add it another 10 times, you get 1 again. And another 10, you get 1. So it would be like adding 1 plus 1 plus 1 infinitely many times, and you're going to get infinity. So the only hope for convergence is that the stuff you're adding goes to 0. Now, don't read too much into that. This is known as a divergence test. It only gives you divergence, it never gives you convergence. Even if the stuff you're adding does go to 0, that does not guarantee that the series converges. Let's take an example. I claim the series 1 over n diverges. First of all, what is that? Let's get a feel for that. This is 1 plus 1/2 plus 1/3, 1/4, and so on and so on. And you see that the stuff you're adding gets smaller and smaller. As n gets very large, this fraction is very small, very close to 0. But even though this term goes to 0, I claim that this series still diverges. And let's show why that is by calculating the sequence of partial sums. We're not going to calculate all of them, but only specific terms. Let's look at S2. S2 is 1 plus 1/2, the sum of the first two terms. And then jump to S4, the sum of the first four terms. And we're going to group these last two terms, replacing them with the smallest number in the brackets. What is the smallest number? 1/3 versus 1/4. 1/4 is the smaller of the two. So let me replace all the terms by 1/4. 1/4 plus 1/4 is 1/2. So this is 1 plus 2/2. And let's look at S8. We're going to do a similar trick with S8, which is the sum of the first 8 terms. So 1 plus 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. I'm going to group these and those. Same trick. In each of the parentheses, we're going to replace all the terms with the smallest one in each. So here, 1/3 and 1/4. Let's replace each of the terms by 1/4. In here, 1/5, 1/6, 1/7, 1/8. The smallest one is? Smallest one is 1/8. So I'll replace all of them with 1/8. What do we get? 1/4 plus 1/4 is 1/2. 1/8 4 times is 4/8, which is 1/2 again. So this is 1 plus 3/2. So you see what's happening, right? This was S. So here we had S2 to the 1, which was 1 plus 1/2. S2 squared is bigger than or equal to 1 plus 2/2. This is S2 cubed, which is bigger than or equal to 1 plus 3/2. And you can repeat with S16, right? You're going to have a next bracket made up of 1/9 all the way to 1/16. And you're going to replace all the terms there by 1/16. You're going to have 8 of them. So you'll get an 8/16, which is another 1/2. In other words, in general, S2n is bigger than or equal to 1 plus n/2. Now remember that a series converges if and only if the sequence of partial sums converges. You could prove that by induction. I'm not going to ask you to do that. We're not going to discuss convergence in this course, but it would be a nice thing to prove. Absolutely. So S to the 2n is bigger than or equal to this. So as n goes to infinity, since this goes to infinity, there is no hope that the sequence of partial sums converges. So the sequence of partial sums does not converge, so the series does not converge. So you see, this is a nice example of a series where the terms do go to 0, even though the series does not converge. The series diverges even though the terms you are adding go to 0. S, where the subscript is 2 to the n. And that really gives you the flavor of what it means for a series to converge. Right? Whether or not a series converges is really a measure of how fast the terms go to 0. Exactly. Right? Here, 1/n does not go to 0 fast enough to make the series converge. 1/2 to the n does go to 0 fast enough, and we saw that that was a convergent geometric series. let's take a few examples from the book. Questions before we do so? Class ends at 1:30, I believe. Is that correct? All right, so consider this. Does this series converge or not? And if so, what does it converge to? We're going to write out the sequence of partial sums. So S1 is exactly that, right? We're going to see that this is a telescoping sum, very nice. So S1 is the first term, which is 1 over square root of 4 minus 1 over square root of 5. S2 is the sum of the first two terms. When n is 5, you get 1 over root 5 minus 1 over root 6. And observe that the 1 over root 5's cancel out here. Very nice. S3 is the sum of the first three terms. 1 over root 4 minus 1 over root 5. 1 over root 5 minus 1 over root 6. And when n is 6, 1 over root 6 minus 1 over root 7. Again, a lot of stuff cancels, leaving you with 1 over root 4 minus 1 over root 7. Can we see a general pattern arising? What is Sn? Right? Sn is 1 over root 4 minus 1 over, what was suggested? Root of n plus 1. Let's make sure that it satisfies what we were looking at. When n is 1, this would have been 1 over 4 minus 1 over root 2. Not quite right. Somebody's suggesting n plus 4. Let's see if that works. When n is 1, 1 over root 4 minus 1 over root 5. Looking good. When n is 2, 1 over root 4 minus 1 over root 6. Very nice. And so on and so on. It works very well with this. Very nice. And now, as n goes to infinity, Sn converges to? Everyone? Well, let me just write it down. I know that you know it's 1/2. Exactly that. And there it is. So this series converges to 1/2. let's consider this series and let's rewrite it in sigma notation just for fun. It's good practice. Can we find a general term for this? Can we rewrite this as an infinite sum starting somewhere? That'll depend on you. How would you describe these terms? Why is it not 1/2 minus 1 over square root of n plus 1? Well, first of all, the n plus 1 didn't work here because when n was 1, you would get 1 over square root of 2, not the 1 over square root of 5 that you wanted to. Exactly, the n is starting at 1 here. And a few people are suggesting n over n plus 1, where n goes from 1 to infinity. Very nice, right? Let's convince ourselves. When n is 1, you get 1 over 2. Plus when n is 2, you get 2 over 3. Plus when n is 3, you get 3 over 4, and so on. Very nice. Very nice. So a nice exercise here. We've managed to rewrite this in a nice closed form using sigma notation. Now what? What can we say about convergence or divergence? What is this limit? Exactly, diverges by the divergence test because this limit is right. If you factor out an n from the denominator, you get a limit of 1, which is not 0. Exactly that. So this limit is 1, is not 0, so the series diverges. By the divergence test. Very nice. Consider this. Consider this series, and I'm sure you've recognized that what we're actually dealing with is essentially two geometric series. Not only is it two geometric series, but it's two convergent geometric series. So you know that if you have a sum of convergent sequences, then they converge to the sum of the limits, right? The limit of the sum is the sum of the limits. Same thing here, because a series is really a sequence of partial sums. So if you knew that both series converge to begin with, you are allowed to split it up. And if you want to be safe here, you could take out a 0.6 to the negative 1, because that's just a constant. And rewrite both of these as a number to the power n. And here, 0.2, well, negative 0.2 in absolute value is less than 1. And here, 0.6 in absolute value is less than 1 as well. So they are two convergent geometric series. Two convergent geometric series, where they converge to first term, so minus 0.2 to the power 1 over 1 minus a. The other one is 1 over 0.6. And this converges to first term over 1 minus 0.6. There it is. I'll let you clean that up, but there it is. This converges, and we know what it converges to. I think we have time for one or two more examples. Consider 54, a very nice question. Which has to do with the fact that the rational numbers in high school were perhaps defined to you as the set of numbers whose decimals either terminate or repeat. Right? That's how it was defined to me in high school anyways. Perhaps they're still doing that. Right? So the set of rational numbers are the set of numbers whose decimal expansion either terminates or repeats. And when I got to university, somehow the rules had changed, and the rational numbers were now suddenly the set of fractions, a over b, where a and b are integers, and b is not 0. And the question is, how do you reconcile the two definitions? Are the two definitions really the same thing? Or do they represent different sets? It's not clear. It's not immediately clear. And this exercise, number 54, asks us to express the number 0.46, 46, 46, where the 46 repeats, as a fraction. Of integers. So let's understand how to do that. this 46, 46, 46, where the 46 repeats, the first two terms is actually 46 over 100. Right? So that's the first 46 here. And then this 46 is 46 over 10,000 integers. So 0, 1, 2, 3, 4, 5, 6, along with their negatives. And then this 46 is 46 over a million. And so on and so on. Or this is 100. This is 100 squared. A million is 100 cubed. And so on and so on. So if you factor out a 46, this is 1 over 100, 1 over 100 squared, 1 over 100 cubed, which you recognize as a convergent geometric series. What does it converge to? Well, I mean, if you rewrite this, this is 100 to the n. You don't have to rewrite it, but so convergent geometric series. Where the 1 over 100 in absolute value is less than 1. What does it converge to? First term over 1 minus 1 over 100, which is easily seen to be which is easily seen to be (46 over 99). If you have a calculator handy and you do 46 divided by 99, you'll see that you get 0.46, 46, 46, and so on. We have time for one more example, number 51. Very nice example to end with. Question 59 is asking us to repeat with the number 0.999 and so on. So again, let's rewrite this as a fraction. This is going to be 9 over 10 plus 9 over 100 plus 9 over 1,000 and so on and so on. If we factor out a 9, this is 1 over 10, 1 over 100, 1 over 1,000. Or 100 is 10 squared, 1,000 is 10 cubed. So once again, you've got this geometric series here. 1 over 10 to the n. A convergent geometric series where 1 over 10 is less than 1 in absolute value. What does it converge to? Well, you know exactly what it converges to. right? This is 9. This geometric series converges to first term, 1 over 10, over 1 minus 1 over 10. So this is 1 over 10 over 9 over 10. The 10's cancel out. This is 9 over 9, which is 1. The number 0.99999, where the 9 repeats, is the number 1. Very nice. How are we doing here? Questions? No questions? A good place to end then. We will pick this up again tomorrow. As you know, we're going to start looking at tests for convergence. We'll do the integral test tomorrow and work from there. Web work is open. I mean, it's only web work 0 for now. The tutorials start tomorrow. I believe it's 10 to 11. If you are having issues logging into web work, email me. As you know, you will log into web work using your ID number as both username and password. Victoria will post a link to the Zoom meetings on my courses. I will ask her to post stuff today. What chapters in the book match this lecture? I want to say, well, I mean, it's in the pages I've given you. 748 and before. I believe it's chapter 10. I could be wrong here. I want to say chapter 10.1 and 10.2. Can I give you an idea of why 0.999 is, well, I mean, it does not become 1, right? It is the number 1. These are all equal sign. So 0.99999, where the 9 repeats, is the number 1. And why is that, right? I mean, imagine yourself on a number line where this is 0 and 1. This number here, 0 point something something, is certainly going to be less than or equal to 1, right? So it might be somewhere here. But it's closer to 1 than 0.9, right? Because it's bigger than 0.9. And it's also closer to 1 than 0.99. So it's somewhere in here. And it's also closer to 1 than 0.999. So you see, you really have to ask yourself, how far is it from 1? How far are you from 1? And you can keep making the distance from 1 smaller and smaller, and you can conclude that you have to be a distance of 0 away from 1. There are 3 different tutorials per week, right? I mean, it's a tutorial given by Victoria all 3 times, but they're all completely different. Because, you know, I mean, one class here covers essentially 1 week of material. So there is, I mean, the pace is very fast. So keep up with the material, go home and practice the 2 sections we did today, and we'll take this up again tomorrow. I don't know where the book can be bought. I'm sure somewhere online. Again, it doesn't have to be that book. Any book which covers the same material is good enough. In particular, old copies of Stewart, make sure that it's Stewart with that has a several variables chapters, right? Format of the tutorial, I'm not sure. I mean, I'm going to give Victoria complete freedom. She has a lot of experience. She's been a TA for 262, 263 for many years, so she knows what she's doing, and I think students enjoy what she does. So I'll refer back to her as far as what she wants to do in there. So again, if you're having trouble logging into WebWork, first of all, it's ID number for both username and password. Even if you had changed it in 141, it goes back. I mean, this is a completely different course, completely unrelated to 141. So it's ID number for username and password. I will see you tomorrow at 11. Thank you very much. If you've got questions, please email me. In particular, if you've got problems logging in to WebWork. Very good. I'll see you tomorrow. Thank you very much.